why are we concerned with f2 to the power n? Because we are talking about Boolean functions. We have seen Boolean functions in multiple avatars, -1, 1 to the power n to -1, 1, 0, 1 to the power n to 0, 1. Doesn't matter. The important part here, we have seen that switching range doesn't matter much. Now we are going to see that visualizing domain as a particular group, as a particular structure really helps us. And till now, we never use the fact that 0, 1 to the power n can be thought of as a group or as a field f2 to the power f2, and the domain cannot be need not be thought of as f to the power. We mostly what we used was that 0, 1 to the power n is basically a Boolean hypercube. That means it was given a graph structure where we joined edges which were Hamming distance 1 up, right? Those were the things which were joined. Now we want to explore more structure of our domain, right? And this is clear to all of you that this is the one or this is the one which I'm talking about. One way to represent this is f2 to the power n. And as soon as we start talking about this, first question is, what is f2? So can someone tell me?
Field containing 0, 1 with modulus additional modulo 2 as the operational.
Right. So this is the simplest field possible, which has only two elements, 0, 1, and then the operations are plus mod 2 and multiplication. Is there anyone here who is not familiar with f2? Please raise your hand. Okay, that's good. We know what the field f2 is, right? And this is mod 2 calculations. I'm sure all of you understand mod 2 calculations. For example, 1 multiplied by 0 is equal to
0.
And 1 plus 1 is equal to
0.
Right, very good. So this is clear to you. And then we can talk about f2 to the power n. Is f2 to the power n a field?
No.
No, it is not a field. No, f2 to the power n is a field. f2 whole to the power n is not a field. Okay, what are we talking about? f2 to the power n, what do I mean? The elements are basically binary strings of length n. This is our familiar Boolean hypercube, right? All the elements are like that. And then when we talk about constants, so we are going to think about f to the power n as a vector space, right? Remember, we talked about r to the power n. So the difference is going to be that our constants are going to come from field f2 instead of r. That means when I write v is equal to alpha 1 v1 alpha 2 v2 plus alpha n vn, alpha i's belong to f2. Very good. Right? So then they are going to be just 0 or 1. And in this case, v is equal to minus, because minus 1 is same as 1, right? And you can always write vector as sum v1 v2 up to v. Correct, because the 0 ones I can suppress and the ones I will just leave them, right? So this is my vector space where my constants are only going to be 0 and 1. And what are my elements? 1, 1, 0, 0, 1, strings like that. Correct? And then how do I add up vectors in this? What is the addition of these in this vector space?
Bitwise XOR.
Sorry?
Bitwise XOR.
Bitwise XOR. So the least significant bit is
1.
1, this is 1, this is 1, this is 1, and this is 0. Okay, so this is the structure we are talking about. This is f2 to the power n. Right? This is the vector space we are talking about. Is there anyone who has not seen this vector space before? Everyone has seen this?
So why do we call that? Why have we written that it is not a field? F2 to the power n.
f2 to the power n. Oh, if it's not my prerogative to prove that it is a field, you give me the operation under which it will become a field.
Element wise, these additions and multiplications.
Element wise addition and multiplication.
Yeah,
Okay.
the element wise addition modulo 2 and multiplication modulo 2.
Okay, you look at the constructs of the field. Can you divide?
No.
Then
Like
1, 1, 0, 0 is sorry. So I'm just saying that you can have 0 divisors, right? 1, 0 into 0, 1. This will give you 0, 0. Right? By your definition. So I have a 0 divisor. A field cannot have a 0 divisor, right? So yeah, so this is and you cannot think of it. You have to give it a polynomial structure, and then it will actually be f2 to the power. Before that, you cannot think of it. Did I answer your question with it?
got it.
Okay, so we are going to look at f to the power n as a vector space, right? So the number of elements in this vector space are
2 to the power.
2 to the power n. Okay, what are the basis vectors, Debarsho?
Sir, 1 0 0 0 0 1 0 0 0, and only one element will be 1 and all will be 0. So there are
Very
n basis vectors.
This is called the standard basis. You can think of many more bases. This is called the standard basis, right? What about the dot product? Can we define dot product here? Anyone? Aditya, Vatsal, you want to take a guess at what is the dot product in this vector space?
Euclidean dot product, I mean.
Yes, just the Euclidean dot product, but then you take it mod 2, right? So if I have two vectors, x1 to xn, y1 to yn, like the real case, I take the entry-wise multiplication, add them up, but then I just restrict it to mod. This is the dot product between x and y. Okay. And then I can talk about vectors being orthogonal and things like that. Right? So tell me, how many vectors are perpendicular to this vector? The all ones vector. How many vectors are perpendicular?
2 power n minus 1.
Why?
Because number of vectors with Hamming weight even.
Okay, good. The number of vectors with number of ones being even or Hamming weight being even, those will be perpendicular to V, and we know that half of the such vectors are like that, right? This is equivalent to what in Fourier language? See, what is V11111? Okay, sorry, I shouldn't say this. So I'm sorry. This is in n. This is n dimensional. This is not 2 to the power n dimensional. Sorry. Yeah, that is my mistake. Yes. No. Can't write it as chi s. That would be into the power n. But yeah, number of ones are even. But it's the same kind of calculation where you just take any one entry, and then when you switch the value, then half of them will be 1 and half of them will be -1. So okay, so what about this vector? How many vectors will be perpendicular to this?
One plus 2 to the power n minus 2.
No.
It's the same, I guess, 2 power n minus 2.
Right. Why?
It's because of rank nullity theorem.
Okay. Okay. But look at it as a simple proof, right? Look at any V1 which has alpha 1, alpha 3, alpha n. Correct? Now, this position has two choices, 1 or 0. Correct? And exactly for one of those choices, V dot V1 will be 0. Do you agree?
Yes, sir.
Right? So this is the same argument which we did even for chi-s. That's what I meant here. If you have in V, since there is a 1 coordinate corresponding to that 1 coordinate, if in V1 I have 1 or 0, one of them will make the inner product 0. In one of them, the inner product will be 1. Remember that your inner product cannot be anything else except 0 and 1 in this f to the power n. The inner product is either 0 or 1, and this is showing that you can club your vectors into pairs where one will give value 1 and other will give you 0. So you can always pair up your vectors v1, v2 such that if v dot v1 is equal to 0, then v dot v2 is 1, and vice versa. So clubbing that shows that the number of vectors orthogonal to it is exactly to the power n. So the only vector where you have more orthogonal vectors is 0, 0, 0. In that case, all the 2 to the power n vectors are orthogonal. Sounds okay? And I will go to the rank nullity, which already has been talked about. Since we're talking about vector space, we can talk about subspaces. But first, what are subspaces in f to the power n? Is every subset a subspace? Can I say that every subset in f to the power n is a subspace?
No, I mean,
Why?
if it does not have an identity, if it does not have the identities.
Okay,
vector,
so I take a subset, every subset which has identity 0, 0, 0, 0, 0. Is that a subspace?
no, I mean it has to satisfy the axioms of vector space.
Okay, so can you give me an example of a space, of a subset which is not a subspace? It should include identity. So I will start with 0, 0, 0, 0. Right? 0, 0, 0, 0 is the identity.
Yeah. So say supposing Hamming weight, I mean 1, 0, 0, 0 and 0, 0, 0, 1.
Right. If I talk about this, then clearly this is not a subspace because
The addition of the last two elements.
correct. This vector is not present. That is why this is not a subspace. Clearly, there are subsets which are not subspaces, but every subspace is a subset. That we agree with. That is how we define subspaces. But now let's talk about size of subspaces. in f to the power n. What if the dimension is 0? If the dimension is 0, then this is the vector space. Dimension 1. What will be the size of subspace of dimension 1? 2. Why?
These 0, the entanglement and the standard vectors of any
Identity
vector.
and even.
And even? What even?
I mean 1 0 0 0 0.
No, so the second thing could be anything. It could be
Yes.
any
I mean,
favorite.
it could be anything. I
any
just
vector.
gave an example.
Right.
Yeah.
But in this case, why is that enough? Because if your basis had just one vector, your dimension is 1, that means all your vectors will look like alpha 1. And alpha 1 can take how many choices?
2 choices.
2. So for alpha 1 equal to 0, you get identity. For alpha 1 equal to 1, you get basis. This shows that the size of dimension k subspace would be
2 power.
2 to the power k.
power k. If the basis is v1 to vk, then every element can be written as alpha k. Correct? Sounds good. This is
So could you repeat the argument once?
sure. If the vector space has dimension k, that means it has a basis of dimension. If the basis is v1 to vk, then by the definition of vector space, any vector v in the subspace should be written as alpha 1 v1 plus alpha 2 v2 plus alpha k. So how many choices for alpha 1 to alpha k are there? Each of alpha 1 to alpha k is a member of 0, these are the constants, and constants come from f2. That means there are total 2 to the power k choices. Now, why would each of them give a different vector?
Because their basis.
Because the basis is a linearly independent set.
Exactly. So if it turns out that this is equal to beta 1 v1 plus beta k vk, then it has to happen that alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, so on and so forth, till alpha k is equal to beta. If that doesn't happen, that means I have a linear combination of v1 to vk, which is equal to 0. It shows that v1 to vk are not linearly independent. That means they do not form basis. Keeping ourselves in a finite field keeps the structure of the vector space also very, very simple. We can have these counting algorithms. Okay. Is this now clear? Dimension k means there are going to be k basis vectors. And then I can write every vector in terms of those k linearly independent. They will all look like this. Take a subset of these k vectors, addition of that is going to be my vector. There will exist a subset of v1 to vk, addition of that will give you the vector in the subspace. Questions? Good. Now, since we have talked about subspaces, we can talk about orthogonal complement also. What is orthogonal complement? If I pick a subspace of f2 to the power n, then A perp is the set of all elements such that gamma dot such that they are all orthogonal to x. Okay. So this is something which we had seen for dimension 1, right? If A had dimension 1, that means it had the form of all zeros and some vector, right? These were all the dimension 1 vector spaces. What were the number of elements which were perpendicular to this? What were the number of elements which were perpendicular to V?
2 to the power
to
n
the power n minus 1.
2 to the power n minus 1,
minus 1.
right? How many vectors out of these 2 to the power minus n minus 1 are perpendicular with everything in A?
All
Sorry,
2 to the power n minus 1.
all to the power n minus 1, right? So that means A perp is going to have the number of elements in A perp is going to have 2 to the power n minus 1 elements. That means the dimension of it is going to be
N minus 1.
what?
N
What have we
minus 1.
forgotten? What have we forgotten in this? We haven't shown what
There it is
Is a
subspace.
subspace.
is a subspace. But can I trust you on that? Can you prove that A perp is going to be a subspace if A is a subspace?
Because
It will have
linearity,
identity for you.
Yes.
I mean, linearity of inner product can.
Exactly. It is very, very simple. All of you can do it. So first thing to remember is that A perp is a subspace. Knowing that we kind of saw that if it had dimension 1, then the perpendicular subspace had dimension n minus 1. In general, if the dimension is k, you can easily show A perp has dimension n minus n. Okay, so A will have 2 to the power k elements. A perp will have 2 to the power n minus k. If k is the dimension of A, obviously, right? This is dimension. Questions about this? You can take it as an exercise and prove later. But if think of it this way, right? Now you will have k vectors in A. So you want something which is perpendicular to v1, v2, vk, all of them, right? Not just v1. And then you can apply induction. You can do multiple techniques, and you can show that the number of vectors that are perpendicular to k such vectors is 2 to the power n. Okay, I'm not proving it, but again, you can prove this. And then now, what is A perp perp?
A.
We see that in other vector spaces also, and here also, this is going to be the case, right? So clearly, every x is perpendicular to gamma. So that would show that A is a subset of A perp perp. Correct? Every element in A is perpendicular to every element in gamma. Correct? So the only thing to show is that if there is an x such that x dot gamma is equal to 0 for all gamma element of A perp, this implies that x is actually element. Again, this is a simple exercise. You can try it. Okay. This is what shows that A perp perp is actually nothing but. One side is really, really obvious that A is contained inside A perp perp. Other thing to show is that if something is perpendicular to everything in A perp, then it had to be in. Right? Just look at the basis of A and just you take the arguments, and this will give it to you. Okay. Questions about this subspace, these subspaces, the orthogonal complements in this subspace? Questions? So the subspaces have very, very nice structure here. We will remember we can count the number of elements too. And we can define subcubes of f to the power n also. This is, in some sense, coming from our intuition of the hypercube. What is a subcube? A subcube is a set of inputs where certain coordinates are fixed. Okay, your every input is x1, x2, xn. You pick a subset, let's say x2 and x3, and picks x2 equal to 0, x3 equal to 0. All the inputs which satisfy this will form a subcube. This is the general way to come up with a subcube. You have x1 to xn, pick your favorite coordinates, pick your favorite variables, assign them a value out of 0 and 1. You fix those, others can take the remaining, right? And that would be the subcube of F2. So if you fix k variables out of n, what will be the size of the subcube?
2 to the power n minus k.
Very easy, right? Fix k variables, then there are n minus k variables remaining. That will give rise to 2 to the power n minus k. So every subcube has size 2 to the power n minus k. And one of the good example of a subcube is the set of inputs in your decision tree. Remember, we had decision tree x1, then 1, 0, x2, so on. And if you look at a leaf, the set of inputs which will come to this leaf are actually a subcube. In some sense, subcube definition is motivated by this, right? Because what are the set of inputs that are coming here? Where x1 is 1, x2 is something, x3, and so on. You are convinced, right? That set of inputs coming to the leaf is a subcube. Yes, no?
Yes.
Is definition of subcube a problem?
No.
Okay. Now we have learned two things: subspaces of f to the power n, subcubes of f to the power n. Correct? These were two different objects which we have thought of, but we kind of saw that all the sizes were always power of t when we talked about subcubes, when we talked about subspaces. The natural question which someone might ask is every subcube a subspace?
No.
No, I guess.
Okay, good. Can you give me an example of a subcube which is not a subspace?
If I pick some bit to be 1, then my identity won't be in the subcube.
Very
It
good.
can't be a subspace.
So think of a subcube which has x1 equal to 1. And you will see that that is not a subspace because 1, 0, 0, 0, 1, 1, 0, 0, 0. If I add these, I will get a 0 at the first place. That means the addition is not in this space. It does not have identity. That's the easy way. But even it is not closed under addition. Right? So this is showing that a subcube need not be subspace. Actually, it will only be a subspace when everything is, whatever you are setting, each of those variables are actually exactly set to 0. Then it will be a subspace. Is every subspace a subcube?
No.
Can you give me an example?
Yeah, I mean all 0 vector and all 1 vector. I mean dimensional.
Very good. This is a subspace. This is a subspace spanned by the vector 1, 1, 1, 1, 1, 1, 1. It has two elements. It's a subspace. Is it a subcube? You can't set anything so that you can't set any subset of variables such that the only two elements you will get is this. This is not possible. Good. Right? So there are two different concepts. A subcube is not a subspace. We have seen, but it is actually a very, very something which is very, very close to a subspace. Do people understand what is an affine subspace? How many people know what is an affine subspace? Raise your hand. Okay. Okay. So actually, my claim is that all of you know it, but probably don't know the name of affine subspace. Okay. Let's look at 2 dimension. What are the subspaces of dimension 1 in this plane? I am talking about R square. For a few minutes, forget about F. This is the plane R square. What are the one-dimensional subspaces of this?
Lines passing through origin.
Does everyone agree? Okay.
Yeah. Any line,
My
yeah.
sorry,
Yeah. Line passing through.
line passing through the origin. These are the only subspaces. But if you look at any other line, this is also kind of a subspace, right? This is just a translation of a subspace. And these things are called affine subspaces. These are in some sense translated subspaces. That means every element of A, an affine space, affine subspace A can be written as H plus A. Here H is a subspace, like a line passing through the origin, and A is the translation. I write it in the set notation like this, but that means I take any vector X and H and add the set of all such elements is the affine subspace, right? So in this case, this would be H plus.
So could you explain how this line is a subspace of R2?
The line is not a subspace. We call them affine subspace. Which one? The passing through the origin or not passing through the origin?
Yeah, passing through the origin.
Why is it a subspace?
Yes.
Oh, take any vector. Every vector is of the form alpha v, right? If this vector is v,
Yes.
then every vector is of the kind alpha v. Right?
Yeah.
This is a subspace.
Okay.
Right. And now the thing to realize is that, yeah, subcube and subspaces look similar, and there was a reason for that. Our subcubes were affine subspaces. Not every affine subspace is a subcube, remember that, but a subcube is an affine subspace. And can you think of the translation now? So suppose I set x1 equal to 0 and x3 equal to 1. Now the set of inputs which I will get is an affine subspace. What is the subspace and what is the translation?
Basically, x1 set to 0 will be the subspace, and x3 will be the translation. I mean, the one at x.
No. See, if x1 equal to 0 was the subspace, then the size of the subspace would be 2 to the power n. But the affine subspace has size 2 to the power n minus 2, right?
Sorry, x1 and x3 both are set to 0.
Exactly. So the subspace is all the vectors of this two.
Right.
Right? This is my subspace H. And what is A?
Having x1 is 0, x3 as 1, all of the bits are 0.
Correct. This is my. And then this subcube is H plus A. Again, none of these are difficult. I'm just doing it so that you get more practice with this. Right? And now, after I have explained this, is this clear now? Are you comfortable that subcube is an affine subspace? Are there any questions about this? Okay. Everyone is fine? Everyone is not fine. So what is the question? Is the definition of subspaces clear?
Yes, sir.
Yes. Okay. Okay, so give me an affine subspace which is not a subspace, which is not a sub. You want to come up with a subspace. Let's say it is just a affine subspace. Let's say it has just two elements. It should not be a subspace. It should not be a subcube.
Alternate 0 and 1s. So there will be two elements.
Okay.
Yeah. Yes, 0 1 0 1 0 1, and the next one is 1 0 1 0 1 0.
Okay. And what is the translation and what is the subspace?
The subspace is the dimension 1 subspace of all zeros and all ones, and the translation is one of these two vectors.
Very good. This is my H, this is my A, this is my H plus A. You can see that H plus A is not a subspace. Obviously, there is no 0, 0, 0, 0, 0, 0. It is clearly not a subcube because I cannot set any variables, any subset of variables, so that I will get only these two elements. Okay. Sounds good. So we are done. We have to be clear about these three things. This, let's say, is the set of affine subspaces. What do I know about subcubes? Subcubes are inside this, intersect with it, outside this.
Inside this.
Okay. What about subspaces? Subspaces are inside affine subspaces, intersect with it, outside it.
Inside.
Obviously, I can set A to be 0, and then I will get a subspace. Okay. So that means I have to start like this. But do they intersect with subcubes? Do they intersect with, or they are outside it, or they are inside it?
They intersect.
Intersect. Very good. So this is subspaces. And what is this area? These are subcubes where I'm setting some subset of variables to zeros. Correct? This is in some sense a small summary of what we have seen. Okay. So f2 to the power n is a vector space. It's a simple vector space. We can talk about subspace of it, subcubes of it, affine subspaces. And now, just for practice, and I would say just for fun, I will represent parities slightly different. Since gamma was, if I take gamma to be an indicator of the subset, that means if my subset is x1, x2, x4, what is gamma? Vatsal, do you want to tell me what is the gamma? What is gamma? What is the indicator vector for this? Let's say there are 5 variables. Gamma is going to be an element of 0, 1 to the power 5, or I should say f2 to the power 5. What gamma will represent S?
So put x1, x2, x4 as 1 and x2.
1, 1, 0, 1, 0. Correct? This is the indicator vector for S. So any gamma element of f to the power n can be thought of as a subset. And now when we talk about parities, instead of talking about S, I can talk about, and then instead of saying pi xi, I can talk about this. This is exactly if you had converted your 1, 0, F2 things into -1, comma. So this is the same parity function, but now my input x is a vector in f to the power n. It is some 0, 1 vector. So when it is 0, it should correspond to 1, and 1 should correspond to -1, and then I should take the product. Correct? That is the parity by I element of S xi, right? This is our parity. Now each xi, I have changed it by gamma xi. Okay, so I will have a factor of -1 if and only if this particular entry in X is present in S and it is 1. Then only I will get a factor of -1. So these two are exactly the same things. This is just changing from 0, 1 to -1, 1. And now what will be chi beta times chi gamma? Beta and gamma are two vectors in f2 to the power n. They will correspond to some subset S B and S gamma.
Chi beta plus gamma.
Chi beta plus gamma, right? And beta plus gamma will correspond to which subset?
Their symmetric difference.
Very
S beta symmetric difference with S.
Very good. It is the symmetric difference of beta and gamma. Things which are in beta but not in gamma, or things which are in gamma but not. Okay. And if I write my parities like this, my Fourier transform, I can similarly write less. Remember, just I have changed f at S to f at. Okay. And this f at gamma is the Fourier transform factor, right? The number of gammas, you can think of gamma to be f to the power n, but if you know about characters in group theory, the characters form an isomorphic group, and this is the set of characters of f to the power n. But if you don't know about characters, don't worry about it. You can take it to be f to the power n. That is fine. Now, this is saying in one more way, this is again saying you can either represent f in terms of its value on every input, or you can specify its Fourier spectrum. They are just related by the Fourier transform matrix. This is just a basis change, but these two are the same things. You can represent them in the input basis or in the Fourier basis. You have seen this multiple times. And then you can talk about 2 norm and 1 norm even in these new, in this new basis. Now this, what is this equality? What do we know it by?
Parseval's symmetry.
This is Parseval's, right? So all this is making sense, right? This is just saying that 1 by 2 to the power n summation fx whole square. This is f2 square, and this is same as this. Parseval basically says this. Right? Summation. Remember, S we have changed with gamma. And for a Boolean function, this will be equal to 1. What about f at 1? What is f at 1? This is summation over gamma f at gamma. Actually, the absolute value. What can we say about it? Suppose I have a Boolean function. Can it be more than 1?
No.
I guess yes, since the when between 0 and 1, the square is always lesser than the value. So
Correct. So actually, this will always be bigger than 1. Bigger than or equal to 1. Correct? Because f at gamma square was equal to 1. Now f at gamma is less than 1, as Udit pointed out. So the sum has to increase. Now it is greater than equal to 1. How big can it get? Can you bound it using the 2 norm? You know of the inequality which tells me which can bound it in terms of f at gamma whole square.
less than equal to 3 by 2 times.
No. Summation ai, where ai's are positive, or mod ai, I want to bound it in terms of summation ai square.
Cauchy-Schwarz.
Yes, this is called Cauchy-Schwarz. Right? So what will come here? Number of i's, which will be
2 to the power n.
to the power n. So that means this quantity would be bounded by square root of 2 to the power. In general, it can range between 1 and 2 to the power 1 and square root of 2 to the power n, but probably for a Boolean function, this might be special. You can check for addressing, you will get something which is bigger than 1. So f at 1 will be more than 1. Definitely, it can be more than, much more than 1 in terms of n or something. And even there are functions where it can take the maximum possible. And by the way, by Cauchy-Schwarz, you know that it will take the maximum value if every Fourier coefficient has the same value. And this happens. If you look at inner product, every Fourier coefficient has this value. And that's why it has the maximum f1. This is the intuition which you should have when you talk about 2 norm and 1 norm. Given a fixed 2 norm, f1 norm will be low if when will f1 norm be low?
When it is concentrated or something.
Or, yes, when it is concentrated on just
When
one.
the 2 norm is
When the entries are concentrated just on one vector. Like so, v1, v2, vn, you know that their 2 norm is 1. The only case when v norm is equal to 1 is you pick a vi and assign it. This is the smallest one. And when will it have the largest 1 norm?
When it is equally distributed.
When it is equally distributed. Okay. Again, don't worry about these things are all, if you sit down and try to prove them, you can. But these are true for any 2 norm, 1 norm thing. We are talking about Fourier coefficients. So what I'm saying is something which you have seen before. I can think of my function as a vector. And once I see it as a vector, I can talk about its 1 norm or 2. And this f at is a vector in what space? I say f hat is a vector. It is a vector in what space?
R2 to the power n.
Yes, R to the power n. Don't get confused and say F to the power n, right? F2 to the power n. No, it is an R to the power n. Every Fourier quotient is going to be some real. Okay. Good. Now we have looked at F2. We have looked at the Fourier coefficients. We know the Fourier expansion. Let's try to create Fourier expansion for a subspace. What does it mean to create Fourier expansion for a subspace? Pick a subspace of F2 to the power n and then look at the function which indicates this subspace. That means it is 1 if x is element of A, 0 otherwise. Right? This is the natural definition of a function which indicates a subspace. Okay, and now we want to find the Fourier expansion of this function. Right? This is again also a Boolean function. 1 to the power 1 subscript A is a Boolean function, and we are interested in finding the Fourier coefficients of this indicator function. Is the task clear? Questions? Okay. Now, knowing that A perp is equal to A, remember that x is element of A in if and only if it has 0 inner product with every element of A. Right? Knowing this now, we can come up with the Fourier expansion of, and this is the simple Fourier expansion of. It turns out to be very, very simple if you talk about A. And why is that the case? Okay, let's think about it. I am claiming that 1A is equal to this. That means I have to show that if x is element of A, then 1AX should be 1. When x is not an element of A, then 1AX should be 0. And my claim is that this is the correct form. Right? If x is element of A, then what is the value of chi gamma x?
1. I mean, it will be 1 for all of these. So the
Exactly.
sum will come out to be 2 power k.
Exactly, because gamma dot x is 0 for all gammas. That means chi gamma x is equal to 1 for all gamma element of paper, implies I will get a factor of 2 to the power k, it will cancel out, and 1a of x is equal to 1 by 2 to the power k into 2 to the power k. Sounds good? This is proving that 1a gives the correct answer when x is element of A. And when x is not element of A, it will also be a similar argument to what we had seen. We had found a coordinate which was non-zero, and then we had argued that half of the things will work, half of the things will give me 1, half of the things will give me 0. The same argument will be applied here. If x is not an element of A, this means there exists some element gamma in A perp such that gamma dot x is. Again, this is following from the fact that A perp is equal to. That means if x is not in A, x is not in A perp, implies there should exist some gamma element of A perp such that gamma dot x is not equal to 0. questions about this calculation? This is something which will happen in R to the power n also. This is just the vector space things which we use. I am using it in F2 to the power. In the case of R to the power n, it would be gamma dot x is non-zero. Here, I'm taking it to be. And once I have a gamma, now I can divide my aper into two parts. Or I should say, I can divide my aper into pairs where each pair will give me a different vector. So I shouldn't say here x and x plus gamma, because x I'm using as the thing which is not an A. So for some y's, I should say y and y plus gamma, right? And now 1a of x is equal to 1 by 2 to the power k gamma element of aper chi gamma. But this I can write it as pairs y chi y of x plus summation over y chi y plus gamma of x. And now these two things will, what do I know about these two things?
They will cancel out.
Right? Because this is
R dot
minus
x is
1 to
one.
the y dot x. And this is y dot x plus x dot. So they will have a different sign. Right? So what we did for subcubes, right? We said that, oh, if we fix some variable, not subcubes, but you remember we did this. If we take a vector, how many things are perpendicular to it? We said, take a vector, there is a particular entry which is 1. It's the same idea. You take the now instead of just one vector, you are taking a subspace, and you are saying that, you know, half the elements of the subspace will give you inner product 1, half the elements of the subspace will give you inner product 0. And that is why these summation x chi gamma will cancel. This shows that we can write the Fourier expansion of subspaces. Questions? Did it go too soon? Did it go fast? How many people are fine with Fourier expansion? Raise your hand if you are fine with Fourier expansion of indicator subspace.
So could you explain again this union part once?
Sure. So see, this is in general true for a subspace in F2 to the power n. Right? If you look at any subspace of F2 to the power n, right, you have some subspace S, let's say. S is gamma 1, gamma 2, gamma k. Okay. Now you know that 0 is going to be element of S. Pick your favorite non-zero element in S. Let's call it gamma. Okay. So 0 and gamma, call it one pair. Now pick gamma 1. Can gamma plus gamma 1 equal to gamma 1? What does it mean that gamma plus gamma 1 equal to gamma 1? It means gamma 1 is 0, right? Debarsho?
Yes.
Right? So this this is a different pair, right? If I pick gamma 1 to be not in 0 or gamma, I'm getting a new pair.
Yes.
So keep doing this. Take now gamma 2. Suppose gamma 2 hasn't come out in these 4. Now gamma plus gamma 2 will be something else.
Okay.
Because gamma plus gamma 1 plus gamma 1 is again, gamma plus gamma 1 plus gamma is again gamma 1, right? So these pairs are self-duals, right? They map to each other under addition of gamma. Right? So that way you can divide the entire subspace into two parts.
Okay.
Okay. Remember when we talked about all the elements which were perpendicular to 1 0 1 0 1 1 0, right? What did we say? Alpha k minus 1, now 0/1, alpha k plus 1, right? So
They will cancel.
right. So we divide it into pairs. One of them will give me 0, one of them will give me 1.
Yes.
And the same thing is going to happen here. One of these things will give me, out of y and y plus gamma, one of the things will give me inner product 1, one of them will give me inner product 0. So okay. So before that, just to divide it, just follow this VD process. Pick an element, add gamma to it. That's your first pair. Okay, and now no other element can come to this except these two, right? Because they are their self-image. So you can keep doing this process and keep taking out pairs.
And how are they canceling out? So
see, y and y plus gamma, right? What is y plus gamma plus gamma?
why?
Y. Sorry, canceling out, you meant canceling out in the bottom?
Yes.
Slide?
Yeah.
That is what I said, right? Like if you look at these two elements, one of the chi y is minus 1 to the power y dot x.
Yes, and it
And
is.
chi of yes. So and I know that x dot gamma is 1.
Okay, so it will change the.
It will change the sign.
Yeah. Okay.
It is the exact generalization of this top thing which we showed. That one was shown for one-dimensional subspace. Now I am showing it for bigger subspace.
Yes.
I think it's right. Okay. And similarly, I can write the Fourier expansion for affine subspaces, not just subspaces, but even affine subspaces. How do I do it? Remember, for the subspace, we used this characterization. A perp is equal to A. That means X is element of A if and only if gamma dot X is equal to 0 for all gamma element of A. This is what we used so that we could indicate, we could give the Fourier expansion of the integer. Now, for the affine subspace, you can see a similar characterization. Instead of gamma dot x being equal to 0, it will become gamma dot a, obviously, right? If I take gamma dot x plus a, gamma dot x plus gamma dot a. This is 0 because gamma is in subspace, h per, and so if you take any vector in A, capital A, x plus a, its inner product with gamma should be gamma dot a. And the opposite will still be. Right? So what we have shown is a characterization of affine subspace, like the subspace. For subspace, the characterization was like this. For affine subspace, the characterization is at the bottom, and you can see the similarity. Once you know this, you will again get the Fourier expansion. Notice when we did it for a subspace, this factor was not there, right? So this is, if you are, what is happening here? If X is element of A, remember A was H plus A, right? Now what will happen? If X is element of A, then X plus A